Hey everybody, welcome back to Price Analysis, a fundamental approach to the study of commodity prices. We are in chapter 17 now, the final real chapter of the book, and we are going to be doing a few videos on the exercises from this chapter. So let me navigate down there. And what we're going to try to do is use a really simple regression model to forecast the crack spread. But it's going to be a little bit different setup than what we used to forecast hog prices in the last chapter. We're going to try to take advantage of the fact that the crack spread, or the profitability in refining crude oil into gasoline and diesel, that process is usually stationary and hopefully maybe a little bit more easy to predict than straight up trying to predict daily returns. So we'll see if we can do better or not, but we'll give it a shot. Okay, so what we're basically going to do is we are going to forecast the crude oil crack spread, and we're going to use a time series econometric technique on the NYMEX futures prices for WTI crude oil, RBOB gasoline, and ultra low sulfur diesel. And we're going to use those futures prices because that's basically the easiest prices for us to go and get. So that's the way we're going to do it. So the regression model that we're going to use is we're going to regress the crack spread on one lag of the crack spread plus a second lag of the crack spread plus one lag each of all the component prices. Now, I just kind of made a judgment call on how many lags to include. If we were really doing a forecasting exercise, there are statistical techniques that will help us choose the appropriate lag length using things like what's called the Aki-Iki information criterion or the Bayesian information criterion. But for our purposes, we're just going to go straight up with the regression model that's here. So keep in mind, you could play with this model and perhaps do better than we're going to do. But we're just going to go with this specification. Specifically, we could add more lags to the crack spread or more lags to these individual prices. Then your model gets bigger, and oftentimes adding more and more lags doesn't help you out that much, especially in a price forecasting context, because we've talked about how prices usually at least approximate the efficient market hypothesis, in that old prices don't help you forecast the next prices very much. So next, let's get some terminology out of the way. When I say the crack spread, I'm going to be talking about the crack spread that is defined up in equation 1 that we talked about in the lecture videos previously for the videos for chapter 17. And so the variable that we're regressing on the left-hand side and the lags of it, the first part of the right-hand side, is literally this and the data that we plotted in the lecture before. So that explains how we get these crack spread variables, and once we've built the crack spread that will go on the left-hand side, we'll just lag that variable like we did in the last chapter to create crack spread t-1 and crack spread t-2. Next, let's talk about these variables on the second row. You may or may not have seen this kind of notation before. If you see delta crude t-1, that's literally just shorthand for the first difference of the logged prices. So delta crude t-1 is the log of crude t-1 minus the log of crude t-2. And we're going to have one of those for each of the components of our crack spread. So now let's talk for a minute about whether or not this specification is going to be statistically appropriate. So you probably remember when we did our forecasting exercise with the ARP model, we spent a lot of time talking about stationarity of the time series variables, and how it was really important to make sure when we were doing our regression model that our data were stationary. And if we tried to regress a non-stationary variable on another non-stationary variable, the t-test will tell us that it is absolutely very statistically significant when it's really just a spurious relationship, and there may or may not be anything to that correlation that we detected. So that same logic applies here, and that explains why we're using logged changes of prices here for the component prices in the crack spread. But notice we're not doing delta crack spread itself, and there's a couple reasons for that. One is when I just eyeball this data, it doesn't really look non-stationary to me. It kind of looks pretty much stationary, like it's kind of floating around some kind of long-term mean. Although in statistics and in forecasting, eyeballing it is rarely enough, we could and we should, if we were really doing a real forecasting exercise in a kind of circumstance that had any consequences, we would go off and perform something called the ADF test, Augmented Dickey-Fuller test. That's referenced here. So if you go and take a time series econometrics class, you'll learn how to do that test. And it basically is for telling you whether your data are stationary or not. So we could do that, and I'm pretty sure we would find that that crack spread variable is stationary. The other thing is, the other reason I have confidence in that is if you think about what the crack spread is it's literally the profitability of refining in the U.S., roughly speaking. It's sort of a gross profit margin for refining crude oil into gasoline and diesel fuel. And it just seems very unlikely to me that we would find a variable like that could drift indefinitely higher and higher in a non-stationary way. The reason for that is we know that the refining industry is pretty competitive in the economic sense. There's a lot of players, a lot of price competition. And markets like that don't usually exhibit profit margins that just grow and grow in a random walk looking way. Usually profits in that kind of a business happen to be looking very stationary, because if there were extended periods of growing profits, we'd see more people entering in the refining business. If there were extended periods of losses, then we would see people exiting. So that kind of long-run equilibrium pressure tends to keep spreads that represent productive processes or gross profit margins in real businesses, tends to keep those kind of spreads looking fairly stationary. Still exhibit volatility, but not the same way that we would see from a non-stationary time series process. So, since we're confident that the crack spread is a stationary variable, we're free to include it in the regression in levels.